Okay,
it's
good.
telling us
Yeah,
now. Yeah.
okay, yeah. So this is my pleasure to introduce Simon Harris. Simon, just a little bit of history. He got his PhD and I believe all other degrees from Cambridge University, and then he spent most of his time before, I believe, in Europe. He was a professor in France and then professor in UK in Bath University, and in Bath University he was very active. In Bath University they have very strong probability group. He was one of major facilitator and creator of ProbLab, which is well known in Bath University in UK and everywhere. But several years ago he moved to New Zealand, where he is just with University of Auckland. And because New Zealand is quite close to Australia, he's very often visiting us and was very kind to attend a couple Australian mass conferences, probability sessions, which we organize. And so I consider this really as a very good opportunity that he can talk to us. And as I know, Simon will be given another talk approximately in 1 month at Melbourne University, but just face-to-face. So if you are in Melbourne, you can come to that talk as well. But anyway, Simon, you are very welcome.
Yeah, thanks very much. Yeah. Yeah, time has flown by. So I think it's over 5 years that we've been here now. No, 6 years. Oh my God. Yeah, time has flown. So I must say it is very nice that I've after post-COVID that I've discovered the probabilists in Australia are not so far away, because there's not so many in New Zealand. So I do hope to continue visiting you all many times in the future. Okay, so thanks for the invitation. So I want to talk today about a project that has involved quite a lot of collaborators of mine over a number of years now, and hopefully I'll get on to some of the latest developments. I'll probably start at the beginning and try and explain the basics of the story, and then discuss, say, some of the later developments and ongoing work. So this is in particular we've got a Marsden. I got a Marsden just over a year or so ago. So of course now we have to make good on all the promises of everything I said I would prove. Okay, so what I want to talk about is genealogies of samples from stochastic models, and mainly I'm going to be talking about Galton-Watson processes. So what's the basic question that I'll be thinking about is what does the ancestral family tree look like if I take a sample of individuals from some larger population? So the simplest example, imagine I've got a family tree starting with an initial ancestor, has two children, has 3, and so on. So the population develops, and then at time t, I'm going to take a sample. In this case, I'm going to sample 4 individuals, say, and then I'm going to look back at their ancestry. They've all got a unique ancestry in the population. Follow those ancestors back, but only of the 4 that I've sampled. I'm only going to trace back the ancestry of the 4 that I've sampled. I don't care about the blue ones that I didn't sample. And then I'm going to be interested, so I can simplify this tree. These kinks don't matter, so I can simplify the genealogical tree just of the 4 that I sampled. The times I'll be interested in where the coalescence events. I'll talk about coalescence when I'm going backwards, or split times when I'm going forwards in time. So we'll be interested in describing this tree, this genealogical tree of the sample of individuals. So that's the structure that we want to describe. So of course we need a couple of things. We need to decide on what's the model for the underlying population. So I'll say I'll be mainly talking about a Galton-Watson process today. So we'll have a stochastically varying population. And then, of course, there's many ways that you can sample. Many people have looked at various different ways. The main way of sampling, I'll be thinking about choosing K, a fixed number K, from those that are alive at some particular large time t. So K of all extant individuals. You could choose a proportion of all the extants, or one of the questions we're looking at now is sampling at different times from the population or over the entire tree. And of course, there's other issues, if we've got a types of individuals or location or fitness, that might influence how we sample as well. But I'm going to start with the kind of basic question, which is just a sample fixed K in a Galton-Watson. So I'm sure you're all experts on probability in this seminar, but just in case there's any PhDs or others, I'll just refresh the Galton-Watson for us. So I'm going to be considering, so NT is going to be the number of individuals alive at time t. Each individual is going to live for an independent exponential time of rate r. So the initial ancestor lives some random amount of time exponential r, and then it's replaced by a random number of offspring, which is an IID copy of some distribution, offspring distribution L. So here we got 2, and then this one lives another independent exponentials replaced by 3, and so on. So because once born, all the offspring are evolving independently. So we've got a nice branching property. There's lots of independence for development forward in time. So today I'm going to be mainly thinking about the case where the variance of the offspring is finite. So if you want to come to my seminar later in person, later in the month in Melbourne, then I'll talk about when the variance is no longer finite. That's quite a different story. So for the sake of today, the variance of the offspring distribution is finite. So what's going to be our basic question now I can formulate. So we're going to have a continuous time Galton-Watson process. We're going to condition on at least K individuals alive at some large time t. So I am thinking of sampling at a large time. And then I'm going to choose those K particles that sample at time t, and I'm going to choose them uniformly at random, but without replacement. That's why I want to have at least K alive, because I want to choose them without replacement. If there's not K, I can't choose them. And then the question is, what's the ancestral tree of that sample of K individuals look like? So this, there were some results known about this before we started investigating it. Durrett had done the K equals 2K. So Threya had also looked at this. Neil O'Connell had also looked at K equals 2 near critical. But it kind of got really horrible and messy to do any higher Ks. You could in principle do it, but it was a bit of a mess. So it wasn't really resolved. And then we stumbled upon using many K spines, which is something Matt Roberts and myself had developed some theory about. And in the paper in 2020 with Sam Johnston as well, we kind of solved the general near critical Galton-Watson for any K. And it turned out actually quite nice and explicit. So this will be mainly what I'll be talking about. This was kind of the foundation where we set up the methodology that now we've recently been trying to extend to different situations over the last few years. Of course, I have to emphasize there's many related models and questions that are very similar, related, and a very long list of esteemed colleagues who've worked on related stuff, including Robert and Aldous Popovich, Gerhard Stadler, Lambert and Stadler, Mary Lambert's also did a proof of something similar to us after we'd discussed, and Jason Schweinsberg And there's many more that I don't have time to mention. So it's a well trodden kind of related questions, but this particular one surprisingly hadn't been resolved. So just a reminder of a couple of the basic classical properties of Galton-Watson processes before I sort of move on to some of the results. So of course, if we've got the mean number of replacements is strictly bigger than 1, we're in what's known as the supercritical case. And so there's a positive chance of survival. And if we do survive, then we get exponential growth, and the constant for the exponential growth is given by some martingale limit. So important for us to bear in mind is supercritical, we get exponential growth on survival. On the other hand, if we're in the subcritical, so the mean number of replacements is strictly less than 1, the probability to survive a large time is decaying exponentially fast. So it's very hard for the process to survive a large time t in the first place. But if we do condition on survival, which is what we're going to do to take a sample, then actually we just get some relatively small population. So mathematically, the distribution of NT conditional on NT positive converges in distribution to some limiting distribution of random variable Z. So there's a nice limiting law. There's just a handful left. The case that we'll be most interested in is the critical case. So the critical case, again, it's difficult to survive. The probability of surviving a large time t is decaying like 1 over t. But if we do condition on survive, we get a big population. And in fact, nt over t converges to an exponential distribution with parameter here, 2 over the branching rate times the variance. So the population, again, on survival, conditional on survival, is of order t. It's of order of the large length of the time window times some exponential random variable. So that's just to have that in mind. So what about going back to the sampling problem? So I always like to start with the simplest case, which is how we kind of stumbled on the method that turned out to be quite robust. And the simplest case is to look at the birth-death process and just sample 2. So the birth-death process, any individual alive just splits into 2 at rate beta, or it dies at rate alpha. So the branching rate is alpha plus beta. And if I look at the time of the most recent common ancestor, of just taking a pair of individuals chosen uniformly at random without replacement at some large time t. So I condition the birth-death process to be alive. If it's alive, I want to have at least 2, and I'm going to sample from that. So what happens? So in the supercritical case, where the birth rate is greater than the death rate, so what did we see? We know that if it survives, and I'm conditioning on survival or bigger than 2, we know we're going to have exponentially many individuals alive. So if you pick a couple uniformly at random from a massive population, the chances are they're not very closely related. They're probably related near the start. And in fact, that's exactly what you see. The time of the most recent common ancestor actually converges in law. So you can work it out explicitly. In particular, if you just look at the tail distribution of the time of the most recent common ancestor, it's got this certain behavior, but you can actually write it down explicitly. Everything's nice and explicit for the birth-death. So it kind of fits with our intuition. Massive population, probably not that related. It's back at the beginning, near the start. On the other hand, in the subcritical, they're going to be related near the end. Why is that? Because we saw that it's quite hard to survive. If you do condition on survival or even having more than 2, then there's a very small population and they're just hanging on barely. That small population, if you pick 2, they're probably going to be quite closely related, because there may only be 5, 6, 10, whatever individuals. So this is like an endangered species just hanging on. There's a lot of closely related individuals likely to be there. So in that case, it exactly fits our intuition that the time back from the end, that actually converges in distribution. And again, it can be given explicitly, but it's got a certain tail. There is a bit of a symmetry, but there is a difference. There's like a size biasing, a gamma distribution kind of tail behavior, and this is just pure exponential. So it's just the warm up, but the birth-death process, it was actually very useful to us to look at, because you can calculate everything explicitly. It really gave us an insight, and it also typifies the behavior in the critical case, the more general critical case. So let's move on to that one and think about going back now to the more general Galton-Watson process, but let's stick with criticality. So remember, that's just the mean number of replacements is 1. We're staying in the nice finite variance for the offspring distribution. So, I mean, I always used to think that the critical Galton-Watson, because it's hard to survive, conditioning it to survive was a bit artificial. But actually, if you look at the end result, a critical Galton-Watson condition to survive a large time, it actually gives a very nice and quite natural model for a large population that's got stochastic fluctuations. And actually, you probably remember that if I take my critical Galton-Watson, run for time t, and I scale by t, I scale down onto 0, 1, so I scale the time interval. Actually, what you get in the limit is a Feller diffusion. Well, if I started with a large population, I get a Feller diffusion started at some point x. If I start with a single individual, it's more like a Feller excursion. So this is our underlying. You can think of our underlying population process in the large time limit condition to survive. It's related to the Feller diffusion, and we're kind of going to pick 2. So in terms of the Feller diffusion, it's like we're picking 2 uniformly individuals from this cloud, and then we're tracing back there until they've got a common ancestor, and we're interested here in this time of the most recent common ancestor, ST. So rephrasing that back for the critical Galton-Watson, we'd sample 2, we condition on being alive at time t. What does the rescaled most recent common ancestor look like? So look at the time of the most recent common ancestor of the 2 chosen uniformly at time t, rescale by t. That actually converges in distribution, and here's the tail distribution. So it's got a log in. It wasn't what we were expecting. We did have a panic that it didn't agree with Direct's answer at first, but actually Direct just gave, I think, the power series expansion, which agrees. So this was already known back in 1978, but is included by our later results. So the upshot is, in the critical case, you've got a big population at time t. You've conditioned to survive. There's a big population of order t. Now, actually, you pick a couple. They can be related anywhere in the entire interval. Then it's not at the beginning, like in the supercritical. It's not at the end. They can be related anywhere in the whole interval. And so it's ST over T that converges. Okay, so that was the kind of known easy cases. So the case that had got a bit horrible was, what about sampling K individuals? So now we need a couple of things. We need to know about all the coalescent times. So we need to know the times when there are coalescents for our K individuals at the end. So we've got K individuals at the end. We look at their genealogical tree of that sample. We need to know those times. And we also need to describe the topology, the shape of the tree. So there's 2 things now to do. And if we're in the critical case, we're expecting, if we scale them by the whole time interval, we're expecting that we get something nice for the scaled split times when we squish time down onto the interval 0, 1. So that's what we'll hope for. So indeed, that did turn out to be the case. So there is a universal scaling limit for all the critical Galton-Watson genealogies when we sample K. So as T tends to infinity, those scaled split times, so there's K samples, so there's at most K minus 1 split times. There could be repetitions if there've been multiple mergers, but in fact, they all end up being binary mergers. So, and conditional on NT greater than K, these scaled split times do converge in law to some V1 up to VK minus 1. And there's a nice there is an explicit joint tail distribution for the limiting coalescent times. Okay, it is explicit. It's got lots of terms in we've got to be careful about poles cancelling out and logs, but it is nice and explicit. So that's just for the split times. What about the topology? Well, as I mentioned, it turns out in the limit as T gets very large and we sample this critical Galton-Watson at a K of them at a large time T, that the shape of the tree is actually asymptotically independent of these split times, and further that the ith split, a family, there's going to be different family sizes. A family of size J will be chosen with probability J minus 1 over K minus I, and that will then split into two groups where we decide the number on the left would just be uniformly from 1 to J minus 1, and then J minus that number on the right. So you may already recognize that topology. Well, first of all, it's only pairwise mergers or pairwise splits. So it's only a binary tree that we see in the limit. And this is the forwards. This is the way of describing the topology going forwards in time. But you may recognize that actually it's the same as the Kingman coalescent, which is described going back. The Kingman coalescent, tracing backwards, each pair of family lines is equally likely to be next to coalesce. That's exactly the same as this forward description that we've got in the theorem. So the topology is very nice. It's exactly what we thought it was going to be. It's the Kingman topology. However, these times are definitely not related, well, not simply related to the Kingman coalescent. So the times are more complex, and but the important thing is that the times, they are independent of the precise offspring distribution and the birth rate's been scaled out of here because we've scaled times. So there's no parameters left in here. All we needed was criticality. The mean of L is 1. There's no variance appearing anymore. There's no rate of branching. Those kind of got sucked away, washed away when we did the rescaling onto 0, 1. So this result would say that the first one that kind of we developed a method which turned out to be quite robust for in the 2020 paper. Sam also followed it up with some other related, more general results for Galton-Watson in a nice paper. So a bit of an ugly formula, but there is a nicer way of constructing that and understanding what that genealogy is of the sample. And it's very straightforward. So in fact, what you can do, if you take a sample of size K at large time T in the critical Galton-Watson condition to survive, to get those split times and the genealogy, first of all, you can just choose K IID random variables with a certain PDF, 1 over 1 plus x squared. Then you identify the maximum, and you just renormalize them all by the maximum. So the maximum now is of length 1, but you also do a little time reversal. And then those time reverse renormalized by the maximum. So these are the lengths of all my sticks. if you like, these are the heights of all my ID random variables, but then this one's the longest, so I renormalize everything to be on 0, 1, flip it over. So I get a lot of stick heights, and those turn out to be have the same law as those unordered split times that we saw in the universal genealogy. So it's a very simple construction to get the split times. To get the topology as well, I think this was related to Aldous's construction of the Kingman coalescent. We basically just want a random ordering of the sticks. Any random ordering will do, and a convenient way to give a random ordering, especially if we increase k or anything, is to just assign an IID uniform random variable to each stick, and we just plot the stick of the prescribed height according to the value of the uniform random variable, and then we always join the other sticks back towards the center, the long one, until they first hit any other stick in between. So you kind of start off with the closest ones, go back to the center, join up, then go to the next one, join up as soon as you hit another stick, and that gives you the topology. So it's a very nice little construction. Put another way, and this is actually where we got the explicit formula from. The joint split times can be written as a mixture with some parameter theta and some density theta, depends on k as well, a mixture of a product, so a mixture of independent splits. Once we know theta, we've got independent split times, each with this density 1 plus theta over 1 plus theta 1 minus s all squared. So we can think of the split times as this mixture of IID times. So, I mean, very roughly, I like to think of this as some kind of mixture of sort of time change, slowed down Kingmans. So the IID structure would come if we just had a normal sort of birth-death process, a normal birth process. We had lots of independence, which is, of course, not quite the Kingman. Kingman, when you've got n particles going back, they're merging at rate n choose 2. So really, this is like merging at rate n. So it's kind of slowed down. This kind of gives us the time change. So you can very roughly interpret it like that. So it's not really the same as a Kingman for the times. But you do have this very nice mixture representation. This mixture, this really is like the maximum. This is the law of the maximum, the mixture, and then conditional on the maximum, this is the law of the lengths of the sticks. So the kind of key message, I guess, is that the random population size at the end really mattered. That's what gave us this mixture. If we didn't have the random population size, we had a fixed population size or conditioned on a fixed size at the end, this would go away and we would have just had IID split times again. So this really, the random population size really made a difference. So there are links back with the random time changes to link back to the Kingman coalescent. For example, when you can find it in the Brownian excursion. Oops, not changing. But somehow we've averaged all of those out. We're not referring to any random time change or anything. This is all now explicit. So we've kind of washed these out, and that's what brought in this kind of mixture. So that's and it was doing, this can be evaluated explicitly, which is just using partial fractions essentially to get that rather ugly formula involving logs that we had, but was nevertheless explicit. So just to kind of maybe just relate that formula back. So we looked at the Galton-Watson at large time, took a sample, took the limit as time went to infinity. So I just want to kind of relate that to the Brownian excursion and the continuum random tree, Aldous's continuum random tree. So This is some classical works. So we didn't use this. It's just to kind of put a little bit in context, another way of seeing what we were kind of doing. So if we start with some tree that's come from a critical Galton-Watson, so imagine this is my tree. So my generations, my time is going upwards. So I've got some tree here. So I can turn a tree into a contour function. So every time I go up, every time I start on the left of the tree at the root and I go up, and when I'm going up, I go up. Then when I turn a corner and come down, I go down in my contour, and then I'm going up again, go up again, then I come down. So you just trace out around the tree, and that basically gives you the contour function. Of course, by the time I get down the bottom, I've got back down to the origin. So the time for the Galton-Watson here corresponds to the height in this excursion. What we've got is an excursion. It starts at the origin, it ends at the origin, because I was just looking at one tree. So we can do that for any nice tree, finite tree, and the number of individuals that are alive, or twice the number of individuals, corresponds to the number of visits to that level in the excursion. Why twice? Because you go up and down, so you're always going an up and a down in the excursion, so you double up. So the size of the population as time goes corresponds to the number of visits. So that kind of corresponds to the local time. That's going to correspond to the local time in the excursion at a given height. So what else were we looking at? Well, we're looking at taking a sample. So suppose that in my tree, I took a sample of two individuals, one here and one there. So in my excursion, that would correspond to, say, sampling these two individuals. How do I know the time of the most recent common ancestor of those two individuals in the tree? Well, it's easy. You just look at the minimum in the contour of the excursion between them. So you look for the minimum point, and that minimum point exactly corresponds to the time of the most recent common ancestor. So the minimum between the 2 points tells you the most recent common ancestor. So that's quite nice. So we can whenever we're thinking about the tree, we can also think of in this excursion world, the equivalent. So what we were doing was taking a critical Galton-Watson tree, condition on reaching a certain height, condition on NT being positive, starting with a single individual. Now, if you scale that tree, that critical tree, you end up with what's known as a continuum random tree, Aldous' continuum random tree. This is a very bad drawing of one, but it's a rather fuzzy tree in the limit. Lots of minuscule short branches. What happens to the contour function in the limit when we take the large time limit of the critical Galton-Watson condition to survive? Well, that's easier to see. It ends up looking like a Brownian excursion. What else could it end up looking like? So there's a link now between our continuum random tree Brownian excursion. The local time of the excursion exactly is corresponding to our population size, or a scale population size. So actually the local time of the Brownian excursion conditioned to reach a height 1, which is like living for time t, pre-scaling, that local time is the thing that's a Feller diffusion. The local time is really a Feller diffusion. So of course this is all classical stuff from Le Gall and Aldous, wonderful works. So in terms of our problem, just to put our problem into context in terms of the limit, is we were trying to take a sample of k points from the Galton-Watson process at time t. That's a bit like sampling k individuals from this continuum random tree in the limit, which is the same as sampling k individuals at level 1 in a Brownian excursion according to the local time. But of course, it's a little bit different. We were looking at the limit of taking a sample from the Galton-Watson. So if we take a sample of the limit, okay, they do turn out to be the same. So if I take a sample from the excursion, I'm already taking a sample from the limit rather than the limit of the sample, which we were doing in the paper. So there's a kind of limit swap that's gone on. But this is the relation. So what we were doing is trying to describe these times. This is an alternative way that you would get the same answer. Okay, so just returning back, this was a way of representing or thinking about those coalescence times or those split times of the sample of size K. Either from the Brownian excursion at level 1 or in our Galton-Watson at time t, where the critical Galton-Watson, where we let t go to infinity. We've got this mixture of these IID split times. So very quick idea of how we prove that. So the very rough idea is we first start off with the original Galton-Watson law P, and then on top of that we choose K spines independently in the simplest way possible as like a reference measure. Start at the beginning, the first spine. Every time there's a birth, just pick uniformly from the children. So we kind of enlarge the original measure to have K identified individuals, and then we do a change of measure, what we call QKT, and the trick is to K-size bias with this is the number of ways that you can choose K individuals from the NT. And this, why is this trick turn out to be useful? Because the probability of choosing an individual uniformly at time t, or a given collection of K individuals, rather distinct individuals at time t in the Galton-Watson, is precisely 1 over that. Now, that's not very nice as a denominator to work with. If one bit of the tree branches a lot, then it affects the probability that you chose one of your uniform samples elsewhere. So that brings all this correlation and makes it very difficult to understand because of all the correlations in the uniform sampling that come about. But size biasing the measure by this, it kind of gets rid of that random denominator and actually miraculously makes the life a lot easier to calculate with. So under this change measure with the size biasing, it turns out that we still have the uniform choice property under Q, but it's much easier to do calculations because you kind of replace this random denominator in some sense with something deterministic, with an average. So amazingly, all the dependencies decouple. It still surprises me. And then that you do lots of calculations, and then it turns out at the end you get this mixture precisely by kind of undoing the size biasing, which helped you out to do a lot, and then you just undo it at the end, and that's a lot easier than trying to work without it in the beginning. So that was kind of really why all the correlations kind of get undone by this trick. So that turned out to be quite robust. So what other situations does it still work in? So back in the original paper, we also looked at near critical Galton-Watson processes. So now I'm going to let the offspring distribution depend upon the length of the time when I'm going to sample at size t, large T, but I'm going to let the offspring distribution now depends upon the time that I'm sampling. It's going to be 1 plus a small correction. The small correction is of mu over t. And the variance is going to stay roughly constant. So I'm just allowing this to be slightly, if mu is positive, it's slightly supercritical. If mu is negative, it's slightly subcritical, but only a little bit over the whole time interval, right? There's only a whole accumulated effect of mu over the whole large time interval. this gives, so if I condition this near critical Galton-Watson to survive to time t, then I just get a large stochastically varying population, which is slowly growing if mu is positive, slowly declining if mu is negative. And of course, these are the other Feller diffusions where you add a drift term. So these are related to the classical Feller diffusion with the extra parameter. So what happens is, even in these near critical cases, there is basically a deterministic time change which depends only on the mu and the rate of branching r. So there's a deterministic function, and if I do a time change of the original split times by the inverse of this time of this function, then that exactly gives me the limiting law of the split times. So put another way, if mu is slightly positive, if mu is positive, so we've got slightly supercritical, what did we see? Slightly supercritical. Supercritical tends to make them more things alive, so you tend to be like more distantly related. So the time change basically pushes the likelihood of the split times a bit towards the beginning of the interval. If it's slightly subcritical, then you tend to push the times in this back closer to the end, closer to the present. So there's a nice interpretation, and of course, as I say, a couple of members of the audience did a very nice investigation of sampling, which I enjoyed reading from the Feller diffusion. So already sampling from the limiting process, but I actually think that was starting with a large population as well. So it's a very nice paper. It's very much related to this kind of work. So basically the same genealogy appears in the critical case, the same genealogy appears in the near critical case. That was maybe not so surprising at least up to the time change. But what was a little bit more surprising is when we started looking at a completely varying environment problem. So this is some more recent work with Sandra Palau from UNAM and my Juan Carlos Pardo, who's at CMAT. So change of model slightly. We go to discrete time, critical Galton-Watson, but we do allow the environment to vary, and we're going to again condition it to survive a large time. So what is that process now? So all individuals are going to live 1 unit of time. We're in discrete time. The offspring distributions depend upon the time. So we've got an offspring distribution Lj for every time j. So that we think of that as the environment at, oh, I don't know why I've got k there. I think that should be a j. So at time j. So you can think of this, all of the individuals in a given year, they experience the same environment, so they all have the same offspring distribution. So this might be a good year, we get a lot. This might be a bad year, we get small numbers of children. Then we might have another good year, they all have a better offspring distribution. So the offspring distribution is changing, and we're given that sequence of offspring distributions, L1, L2, L3, L4. We're given that going on forever. So everybody alive at time j gives birth according to offspring distribution Lj independently. So Mj is going to be the mean in the jth generation. Vj is going to be basically the variance in the jth generation, or the decreasing second moment in the jth generation. What's going to be the mean size of the branching process at time j? Well, that's just the product. If we start with one individual, that's just going to be M1 times M2 times Mj. So the mean size of the population at time j in total is just the product of the offspring distributions at each of the times. If it was the same offspring distribution, it'd just be m to the j, of course. What does criticality mean for this model? So we do need some mild regularity. And criticality in this context, this was worked out by Kirsting, and Vatutin's also done a lot in this area. So criticality basically means the extinction probability should tend to 1. So the process should become extinct if it's left to its own devices. But if we do conditional on survival a long time, which is what we're going to do, the population should become large. So we're in the same kind of situation. Criticality kind of means the same thing. It will die out, but if you condition it to survive, it should be a large population of order of the size of time, maybe, well, not quite the same, but it should be a large population. So again, in this time-varying, discrete time-varying environment, that if we condition the process to be alive at a large time, we've got a model for a kind of large, stochastically varying population, but in a varying environment. So we really can have bottlenecks. We can have really bad periods where the population gets small, and then there can be periods where it's growing much better. So it really can be a lot of variation in this model. So to our surprise, there was, or there is, a deterministic time change. So I define a time change, tor n of j is defined to be rho j normalized by rho n, where rho j is just basically the decreasing second moment of the population size of the Galton-Watson at time j, divided by twice the mean squared. So this is quite a natural quantity to look at, this rho j. It's increasing. It's an increasing, you can work it out explicitly. These are the variance of the jth offspring over the twice the mean to date. So that's the mean of the total population rather than the offspring distribution. This is increasing. So we can define this time change. And rho n is the largest. So this gives me a time change so j ranges from 1 to n, and then this gives me numbers in 0, 1. So it turns out if we apply this time change to the times, we run our discrete time Galton-Watson environment, condition it to survive large time to large time n. We take our sample of k individuals uniformly at random from that large population. Those have their split times, S1 to SK minus 1. So we've got K minus 1 split times. If I apply the time change to those, conditional on there being at least K alive at time n, then those rescaled split times converge to exactly the same limiting genealogy as we had before. So it did surprise us that A, we could get the method to generalize, that it was robust enough, and B, that we really did see the same, even in this quite general setting, there really was a time change and we got exactly the same genealogy appearing. So what does this time change mean? I mean, you can kind of interpret it a little bit if this rho j will be large if there's a big variance. If there's a big variance in the population or a low mean at time j, so a big variance or a low mean at time j, then that's going to lead to increased coalescence. So really, it's really, if you plot the time change, places where it increases rapidly, it's going from 0 to 1. So where it increases rapidly, that's where you're going to tend to get coalescence occurring with this time change. So it might have flat bits where there's not really much going on, and then places where there was low population or low mean or a lot of variation, a lot of variance, you tend to get a lot more coalescence events, which kind of fits your intuition. If the population's small, you're more likely at some time, you're more likely to have shared common ancestor at those bottlenecks in the population, or equivalently, if there was a big variance, because it's kind of critical, it kind of forces you together. So you can kind of see these bottlenecks appearing in the time change. So it's quite nice. It's got quite nice interpretation as well, the time change. So we do have to thank Gertz Kirsting, who had already discovered this time change, and we were a little bit stuck, and then we realized that we could massage it into our approach, and get our critical Galton-Watson sampling working. There's also a paper by Bernkus, Futilrodi and Scherzer, who actually look at a kind of near critical version. They use similar but quite different approach, and that's a very nice paper where they actually assume there's a kind of limiting environment. So they assume they've got some convergence of the environment, whereas we've just got an environment that goes on forever. So that was that's the varying environments. Exactly the same limiting sample genealogy appears. It really seems to be universal in this setting, as long as we got the finite variance. So perhaps just to wrap up, so some ongoing research and other stuff we've done. So there's sampling the Galton-Watson with heavy-tailed offspring. So when we lose the variance, basically, again, we get universal genealogies, but in that case, there's multiple mergers. So this is hopefully I'll talk about this in my seminar later in the month in person in Melbourne. So there's a paper with Sam and Juan Carlos where we've done the alpha in 1-2 case. We still don't completely understand this. It's something, well, we think it's something like a time-changed mixture, a mixture of time-changed beta coalescence, but I must confess it's quite a complicated coalescent that we get. So we still haven't really nailed down, understand it fully, but we have managed to characterize it. So I think that's actually already out or to appear in annals of probability. And we're still trying to do the alpha equals 1 case. We've also been with Sandra and Juan Carlos. We're also looking at sampling at different times. So having some fixed times or choosing those times randomly and then choosing population randomly from the population and seeing if we can characterize that. That's quite tricky, but we're getting the machinery up and running. There's also sampling with different types. If you've got a critical multi-type Galton-Watson condition to survive, we already know we're almost finished. So some work with Osvaldo as well. We're just writing up. So again, you get the same limiting split times and topology comes out for the limiting coalescent. But over that, you've got to overlay how the types behave. But again, it actually turns out to be the same limiting sample genealogy that appears even in the multi-type setting. And you just put on the types, everything kind of runs in equilibrium. So you just drop the type evolution at the times of the splits before and after. It's quite a nice little picture, but it's surprising. Again, the same genealogy comes out. We're also hoping to look at sampling according to fitness and location. This was actually my original motivation, was to understand sampling near the tip of BBM. In fact, there's been some really fantastic recent work by Tournier, Bernkus and Scherzer, as well as also been involved. There's several papers here that have been looking at these branching diffusions and some very nice results coming out with related K-spine results. Anyway, I perhaps better stop there, as I can see now the time is short. So thank you very much.
Okay, thank you, Simon. for very detailed talk. So now, if you have questions, just unmute yourself and ask your questions, please.
Very nice talk, Simon. There's some lovely results there. Conrad and I have been working in the fellow diffusion directly. And I guess the way we worked on it was to really look at coalescence in the entire population.
Yes.
And then say, oh, okay, so we're taking samples in that, what happens to the samples? So it's slightly different emphasis in the way that you've gone about it. We also get the distribution of the times in the coalescent too, but I couldn't actually tell just looking at what you had and what we had, what the comparison is. I need to actually have a good look and see what the connection is in that.
Yeah.
I like the beta coalescent very much. I was going to ask you, could you get to the later coalescent, but you've said it already. Very nice. Yes.
Yeah. So I hope that if I will put more emphasis in my later talk on this multiple mergers one, because it's a very nice story, and again the kind of technique, the kind of K-spines technique that we had, it lent itself nicely once we'd done some extra discounting, but. But yeah, I really love your paper with Conrad on the sampling directly from the fellow diffusion, and I mean you had some different tricks that overcame the kind of, we had a different trick of this size biasing that overcame the complications, and I was really impressed that you had a different trick that I didn't like, that managed to do it another way. And I think they are strongly related, but my memory was that you started with already a big population. I mean, you started, so you had the chance that they weren't in the same cluster, that they had different individuals maybe at the beginning, that they hadn't coalesced. So, but I think within the clusters, I think we must be looking at exactly the same thing.
I think we must, yes. The well, with the intercoalescent times, the rate is 1 on sort of k minus 1 again, times a constant. It's this universal kind of idea, but the distribution is very different from exponential.
Yeah, exactly.
That's what you said too. Yeah. It's a
No.
universal thing. But the mean time is actually
oh, it agrees, right? Yeah.
It agrees. Yeah, with Kingman.
Yeah. No, it's interesting. The mean agrees, but so they're kind of close in some ways, very close in some ways, but other ways, a bit different.
The mean time is the same. Must be some sort of mathematical reason.
Yeah, I did. There's still a lot of mysteries that even having worked on this in several years, I said, oh, that's why it works. Finally, I understand. But there's still a few left. Yeah, thanks.
Some other questions or comments?
Simon, hi.
Hi, Ross.
Hi, how are you?
Good, thanks. How are you?
What I understand is that from your Galton-Watson process, as you've explained it, what you reconstruct is something very similar or the same in some respects to the Kingman coalescent.
Exactly. The topology is identical. It really is Kingman topology. But I think the thing that surprised us and was that these times they have some relation, like the mean, but the distribution is really not. It's not directly relatable to the times that you get in the standard, K Kingman coalescent. So I think that was the surprise, that there was this funny mixture of these IID times. It's not really the same distribution as the times you would get in a standard Kingman.
True. The Kingman coalescent is taking one more step. The Kingman coalescent is related with the Ewan sampling formula.
Right.
When you're looking at the the ultimate genealogy. But the Ewan's formula, the Ewan sampling formula, is just one possible way of describing the outcome of a genealogy. There are other more general models such as the Pitman models and so on. And I wonder if there's some sort of way of generalizing what you're doing to those more general models.
Yeah, I haven't looked at that. It would be a very nice thing to look at, definitely. So yeah, I couldn't guess but I mean, so far some of the techniques we've been using, because we kind of construct. So even though you kind of sample at the end and you kind of want to understand the coalescence going back, but what we kind of do is do this change of measure. So we actually construct a forward process that's nice and Markov that happens to have the uniform sampling at the end. So we have this is kind of our approach, is to construct a forward process with the right property of the K being a uniform sample without replacement at the end. And it turns out that it has turned out to be more robust than we kind of thought it should be. So who knows what the limits are going to be, but we would certainly like to look at the kind of generalizations and analogs of the UN sampling.
Yeah, there are ways of iterating back from an observed frequency spectrum back to previous generations, and there may be some way of modifying that. Yeah,
it'd be very nice to look at. There's so many nice, interesting questions. I'm just like slowly going through with. I mean, even there's quite a few of us working on the related area. We're just chugging through slowly. Smart Yaw once said to me, "You like a snail chomping on the lettuce slowly."
That describes a lot of us, I think.
Okay, so I think that probably we stop at this point. Let us thank Simon again. So really for very good talk, and I think it was very good discussion.